do spell it different ways, but like I've never seen a Stacy with the I-E-G, whatever it was.
I think people just make stuff up sometimes just to be funny. Like, how wrong can we make this? But still look similar enough to... I don't know. Alright. Rates of change and limits. Maybe this will sound a little bit similar.
I think it does. You haven't said anything yet, but I feel like it will.
Y equals f of t is average speed. You're going to start to notice this is going to sound a lot like physics class. During an interval of time. So it's going to be distance divided by time.
That's what he was breaking.
Average rate of change. Or average speed. F of t plus h minus f of t all over h
Oh no.
equals delta y over delta t.
No. I remember this from last year and I never understood it.
It's okay, but see, at least you've already had an intro to it.
That's
You're not
very
seeing
true.
it for the first time.
I would, yeah.
We've seen this before.
In our
Yes.
last chapter.
Yeah, in like
pre-cal.
10.3 or something of pre-cal.
It was definitely different variables though. Oh wow.
No, it wasn't.
It's
Oh, wait.
possible these were
Was it?
different letters because
It
whatever
was
the
like
book
an A.
used. Yeah. It probably was A plus H and F
It
of
was.
A. They get used interchangeably. Instantaneous speed is the speed of moving object at a given instant of time.
Actually, one of the
All right. Definition of a limit.
Isn't there like an easy way to? Like,
Yes.
Is this not? Yeah. Which I remember.
This is going to sound extremely confusing,
Nice.
but I promise it's not that bad. Actually, it just sounds confusing. Assume F is defined in a neighborhood
Alright, there it is.
of C. And I swear this is how it's written in your book, okay? This is what I had to prove this in one of my college math classes.
And what?
But I promise you that's how it's written in this book. I'm not going to make you prove it.
Amazing.
What class was that?
A
The
gross.
study of proofs, like what?
Real analysis. No, not real analysis.
That just sounds like
Something like that.
so fun.
Definitely not
Did you have to take a lot of? Did you have to take? I assume you had to take stats, but like,
I had to take calc-based stats. So
What?
stats using calculus.
how do you do that?
Not very easily.
Right.
And it's so annoying because, it can be done with algebra.
What are those like? What are the what, who's, hows, whys, and wheres? Just Please solve with calculus-based formulas.
Let C and L be real numbers. The function f has limit L, so capital L is representing a limit, as x approaches C, if given any positive number epsilon there is a positive number delta such that I would say just write down exactly as it looks on my paper and then go back and write what things mean after. I'll go back and explain it again. Such that for all x, 0 is less than the absolute value of x minus c is less than delta. Or well, if then the absolute value of f of x minus L is less than epsilon. So we write, in a much easier form, the limit as x approaches c of f of x is equal to L.
Why did they have to like be so extra with the definition?
Don't want to feel all smart.
Because technically that is what it means.
And like big words.
But we don't need to do a whole lot with that at this point in math. At Liberty in Calc 1, they make you prove this.
Who even came up with like these math proofs? Like, how would you even go about like discovering?
Like, who was just like, yeah, this is this, and then people around him was like,
I'll
alright,
find
that's
it.
valid. Like, who?
I would have been like,
you
no,
gotta
get
be
that out of my
you gotta be
face.
like a special kind of person to just like want to.
You really just called them out.
They need to be called out. What's an issue?
True, but we wouldn't be able to do things without these things.
Can you throw in my cheese soup? How much do I have found really good juice. So the bacon turkey broccoli thing done. Don't throw in my bag. No. Yeah. Don't throw in my bag. It's throwing it out. That's definitely not what I said the first time though.
You said, yep, no.
So basically, I'm just gonna do it on my phone so but you won't really be able to see it. But that is using the definition with the neighborhoods, which is what,
Was that your college homework?
yeah.
I don't even,
See, where's the
I'm
math?
not even sure what that
Where's the
says.
math in that? All I see is like
I'm not
words,
even sure.
variables and exponents. I don't see it. Oh,
Exactly.
there's a 3. That's about it.
Oh my
Like, how do you even
goodness.
say that's math?
Get it out of here.
Exactly.
Also, have you kept all of your college assignments?
Well, I wouldn't have necessarily, but these were turned in online, so I had to like scan them in. So that's why I have them.
Didn't keep them fun.
All right, I'm gonna go back through this now. So if you want to write down what things mean, not in symbols, you can. Okay, so the function f has a limit L. Okay, so a capital L is always going to symbolize our limit. As x approaches c, if given any positive number epsilon, so this fancy E is epsilon, EPSLON. Something like that. I don't know. It might have an I in there after the S.
I'm not too concerned.
I don't know. As long as you know what it means. There is a positive number delta such that for all x, if 0 is less than the absolute value of x minus c is less than delta, then the absolute value of f of x minus L is less than epsilon.
Obviously.
So rewrite x minus or x as x the limit as x approaches c of f of x is equal to L.
It's so
Like, who doesn't
Obvious-
know that? Like,
obvious, like,
like, that's crazy. I learned this like first grade.
It'll make way more sense when you do it with problems.
Like, I've learned this in like
I promise.
second grade. Like, I don't know what you guys are talking about.
Actually, your book.
I've been deltaing the epsilon. Not epsilon. Wait, that's
Absalom.
that epsilon.
I've been
Epsilon.
deltaing the Epsom salts.
I've been deltaing the
That's good.
epsilon.
So we're not gonna worry about it.
It's first grade.
Yeah.
All right. Now we're gonna have properties of limits. And there's gonna be, well, several of them, I guess technically. Properties of limits. What?
So Jesus told you. Why didn't you say?
The limit as x approaches c of k is equal to k. This is the limit of a function with constant value k. So k is 3, for example. That's all that means. If the limit as x approaches c of 3, then that would be equal to 3. Because there's nothing that you're plugging in, basically. The limit as x approaches c of x is equal to c, because you're plugging in c for x. So this is the limit of the identity function at x is equal to c.
I like these functions. I like these properties.
All right, so it's still part of the properties, but it's going to have a theorem kind of within it. So, theorem, if capital L, capital M, lowercase c, lowercase k are real numbers and the limit as x approaches c of f of x is equal to L, and the limit as x approaches c of g of x is equal to M, then, so that's all just setting it up for the properties that are following. The first one is the sum rule, which says that the limit as x approaches c of f of x plus g of x is equal to L plus M. So if the limit is taken from as x approaches c for f of x plus g of x, then it's just the limit of L plus, or like the limit value of L plus the limit value of M. Difference rule. The limit as x approaches c of f of x minus g of x is equal to L minus M. Product rule. The limit as x approaches c of f of x times g of x is equal to L times M. For the constant multiple rule, the limit as x approaches c of k times f of x is equal to k times L. So basically, if you multiply by pretty much any number, it just is the same as multiplying the limit by that number. Quotient rule. The limit as x approaches c of f of x over g of x is equal to L divided by M, provided the limit M is not equal to 0. As long as M isn't equal to 0, we're good. Six, the power rule. If R and S are integers, with S not equal to 0, then the limit as x approaches c of f of x raised to the r over s is equal to L raised to the r over s, provided L raised to the r over s is a real number. That's the last property. All right, next we're going to have theorem 2, which is polynomial and rational functions. So if f of x is equal to a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 plus a sub 0 is any polynomial function and c is any real number, then the limit as x approaches c of f of x is equal to f of c is equal to a sub n c to the n plus a sub n minus 1 c to the n minus 1 plus dot 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 plus a sub 0. So all that's saying is if you've got a function that's polynomial and it's you have, you know, the terms being raised to a power, whatever, you just plug in whatever value is getting plugged in for the limit. So as x is approaching whatever number is chosen, we just plug that in for x all the way through. Very confusing way to say something really easy.
Yeah, I never understood what that meant.
This is just a
Subscript and
generic form of a polynomial. It's basically just saying that you can have a constant term in front of each number. You don't have to, but that you're like x being raised to a variable, it's just saying it's in order of descending, like descending order terms. So it would be like x cubed, x squared, x to the first, and then there's x to the 0, which is just not there, which is the a to the 0 term, a sub 0 term. Two, if f of x and g of x, whoa, that was a really bad hand sign, are polynomials, and c is any real number, then the limit as x approaches c of f of x over g of x is equal to f of c over g of c, provided g of c is not equal to 0. That's it for that theorem. Next is going to be 1 and 2-sided limits. So sometimes the function will go towards different limits as x approaches c from different sides. Anybody remember when we brought it up last year what would make that happen? Or what maybe the graph looked like? So like we looked at if it came from the right and versus it came from the left.
I'm familiar with it, but I don't like.
If not, it's okay. I'm just
there's a
curious.
negative sign.
There was a negative sign. That was for a left-hand limit.
Oh. No, but I got it. But like I don't know. Yeah.
So a piecewise function would be an example, or like the step function, because it would coming from one side could be one value, and then coming from the other it can be a different value. So a right-hand limit is the limit of f as x approaches c from the right so the limit as x approaches c, and then it's got a little positive sign in the exponent that means from the right of f of x is equal to, and then whatever it is in that particular scenario. Then a left-hand limit is the limit of f as x approaches c from the left So we have the limit as x approaches c, and then in the exponent, there's a little negative sign. That means from the left because it's coming from the negative side of f of x is equal to whatever that respective limit is. And then if we had a two-sided limit, it would just be the limit as x approaches c of f of x is equal to whatever that respective limit is.
Thank you.
How many more pages of this do we have?
Like a third.
Nice.
We have two theorems and then we're done. Let's see, what color do I want? Theorem 3. A function f of x has a limit as x approaches c if and only if, so remember IFF is if and only if, the right hand and left hand limits at c exist and are equal. So this is going to be basically, you may want me to write this first and then you write it. The limit as x approaches c of f of x is equal to L if and only if, so remember the two-way arrows, if and only if. The limit as x approaches c from the right of f of x is equal to L, and the limit as x approaches c from the left of f of x is equal to L. Okay, so it's saying that if the right and left hand limits are equal, then the two-sided limit is equal to the same thing. Okay, that's what that's equal to, and vice versa. It's an if and only if statement. So if one is true, the other has to be true. Somebody pick a color.
Purple.
Lavender.
That's just a shade of.
I know. Well, you gotta pick a shade.
I was gonna.
Theorem 4. I hope you're hungry. This one is the sandwich theorem.
Oh, I thought you meant like it's gonna be.
I mean, I could eat more Panera, honestly.
No, I'm full.
It is the sandwich theorem. So this says if,
That's actually what it's called.
yeah.
No, she just wrote
No,
it
she
for
just wanted to
kicks
write
and
that.
giggles.
Well,
Not
like,
just in Google.
If g of x is less than or equal to f of x is less than or equal to h of x for all x not equal to c in some interval about c, and the limit as x approaches c of g of x is equal to the limit as x approaches c of h of x is equal to L. So if both of those are equal, so notice that's the first and the last thing written here. Those two things, okay? G of x, h of x. Those are equal to L. Then the limit as x approaches c of f of x, so the middle thing, is also equal to L.
Wait, so the outside.
So g of x and h of x. So if the limit as x approaches c of g of x and as x approaches c of h of x, if those are equal to L,
Yeah.
then the one in the middle is also equal to L.
Okay.
Now there's one more thing, and I'm trying to see if I need to tell it to you now. I think I'm gonna wait and tell you this other thing in another section. Don't think it needs to be known yet. Never mind. I'm gonna go ahead and tell you. That way we don't forget. The limit as x approaches 0 of sine of x over x is equal to 1. And that will always and forever be true.
Oh, I remember that one.
I do remember that.
Okay, well, good. We've already seen it before. I think it actually comes into play with the sandwich theorem in one of the problems that we do, if I remember correctly. But I can't see right off the top of my head that that's what it is. So, anyways, that is it for the notes.